So, dear students, in this video, I'll be talking about another application of operational amplifier, and that is that this operational amplifier can be used to measure the log of the input signal. The input that will be given to the operational amplifier. Uh, we can have at the output of this operational amplifier, we will have we will have the log of that input. Operational amplifier as logarithmic device. So to start with, we have an operational amplifier, and it has two inputs. One is non-inverting, another one is inverting. Then we have the output of this operational amplifier, and we have here, instead of feedback resistance, we make use of a PN junction, and here we have the output, and here we have the input resistance, say R, and then we have VI here as input. So here we ground the non-inverting terminal of this operational amplifier. Now this is the circuit requirement of an operational amplifier to be used as a logarithmic device, where the output will be the measure of log of the input. So we would like to analyze this and obtain a relation where we can have an output to see whether it is the logarithmic of input. Now, for doing so, let us assume here we have V1, and here we have V2, and let us suppose the current that goes from here is I, and here we have the current through this PN junction, and let us assume here we have the current I1, and we can immediately think about KCL at this junction. Suppose this junction is P. So if I applying KCL at junction P. So what's going to happen? I'll have I, that's the incoming current, that must be equal to ID plus I1. ID and I1, they are the outgoing currents from the junction P. So in the similar fashion as we have talked about in the previous videos, that the input impedance of an operational amplifier is extremely large. So if its input impedance is extremely large, then the current that can flow between these two terminals, that should be zero. So here I would say that for an ideal operational amplifier, input impedance is infinite. So that implies this I1 term in our equation will boil down to zero. So what we are left with is I equal to ID. So here we have a p-n junction, and this p-n junction, across this p-n junction, there is some voltage. Say that voltage is VD. Okay, and here I have VI. Okay, then I have V2, then I have VD, and then I have V out. Okay, so let's proceed from here. What should I use for I using Ohm's law? For I think it is VI minus V2. For I, so for I have what I have. I have VI minus V2 divided by R. Okay, this is equal to ID is it's the current that's passing through this PN junction, and for that we have an exponential equation for the current through the diode, that is I is equal to IS e to the power of Vd upon eta Vt. Now in this equation, Is is the saturation current, and it's a constant. Saturation current, and it's a constant. Eta is a constant, and the thermal voltage, it's also constant. So they are just numbers. This Is is a number, eta is a number, and Vt is a number. So here, instead of Id, I would write Is times e to the power of Vd upon eta Vt. So one thing is important here, that we have Vd, and what is this Vd? This Vd is the it is the potential difference. It's the voltage across the PN junction. Okay, so if I have to resolve this Vd should be basically Vt minus V2 minus V out. So I can think of this Vd as V2 minus V out. I can use it in above equation. So what I'll get Vi minus V2 divided by R equals Is e to the power of V2 minus V out divided by eta Vt, and eta Vt is nothing, it's just a number, and Is is also a number. So here in this equation, we would like to use the concept of virtual ground, and we can understand that from previous videos, that the potential at V1 is equal to potential at V2, and since V1 is at zero potential, so V2 is also equal to zero. So here we are using what we are using virtual ground concept, and that gives us V1 equals V2 equals 0. So if that's the case, I'll get Vi upon R is equal to Is e to the power of minus V out divided by eta T. All right, so this is it. Now I can have Vi equal to Is or e to the power of minus V out divided by eta T is a number, say that's equal to A. So here I would say that this eta T is A. Okay, so here in this equation we can use log on both sides, and so applying log on both sides, we are going to get log of Vi equals uh, say this is is, it's a number, and it is, I should have brought it here so that there is no confusion. Okay, let's do it on the next page now. Let's proceed from here. What's going to happen? So this is 3. So I can write from previous equation, I can write VI divide by B, okay, equals e to the power of minus V out by A, where this B is a number and this B is what it is, ISR, and A is a number and it is equal to eta Vt. So if this is the case, if I make use of log on both sides, so ln of Vi by B equals ln of e to the power of minus V out by A. So here we are going to get ln of Vi minus ln of B equal to, here we will have minus V out by A, right? So I can write ln of Vi is minus V out by A. Yeah, that's right. And this is this will be plus ln of B. All right, so let me separate this. So negative sign, so let me get this V out by A alone here again, because I want V out only. So let it be like this. So this is ln of Vi plus ln of B. Okay, so V out will be A times ln of Vi plus A times ln of B. Okay, so here you will have minus, and here you will also have minus. And you can boil down the numbers. You are not interested in numbers. Here you can see that V out is proportional to ln of Vi. So this way we can understand that the output that we obtain is the measure of log of the input signal. And the rest of things that are here in this equation, like A, L, and B, these are just numbers. These are the constants. The function over here is Vi. So we are able to see that the output that we obtain from this operational amplifier is directly proportional to the log of the input signal. So this way, this is how we can make use of an operational amplifier to measure the log of the input that's given to the operational amplifier.